Birds and bees have evolved to avoid predators by swiftly untwining predator movements from their own in a highly efficient and reactive manner. They lack the brain capacity to reconstruct their environment like most modern-day robots. Hence, they rely on optical flow by looking at pixel movement. Although optical flow is often expensive and slow to compute, in today's era, their computation can be sped up using neural networks. In this work, we propose a method to make them fast and energy efficient for deployment on tiny robots. Our method requires only 1 watt of power and can run on a tiny robot. Additionally, our method infers 10 times faster than comparable methods, allowing for quicker detection of the obstacles needed for high-speed autonomous flights. We obtain 100 FPS dense optical flow using only 1 watt of power by chunking the image into smaller parts while preserving accuracy with the proposed multi-scale architecture. We evaluate our method on common navigational tasks like navigating through cluttered environments, flying through unknown shaped gaps, and dodging dynamic obstacles. In the first application, we demonstrate the ability to navigate through a cluttered environment. The static obstacles show up as high optical flow regions as the drone moves close to the obstacles. This is used to detect and navigate around static obstacles. For our second application, we can fly through gaps of unknown shape, size, and location. We use an active vision strategy to move around the scene to obtain high optical flow values outside the gap. This is utilized to detect the gap and fly through it. The effectiveness of our fast throughput becomes apparent while dodging unknown dynamic obstacles. The dynamic obstacles show up as regions of high optical flow that can be segmented from the background. To summarize, with our low latency and energy efficient optical flow approach, we can navigate through cluttered scenes, fly through unknown gaps, and dodge dynamic obstacles. We firmly believe our approach can open doors to new levels of autonomy on tiny robots not possible before.